If there are two different ways to break a bond, there are also two different ways to form a bond. So the first method here involves two radicals. So you have two radicals that are coming together to form a single bond. So this single bond right here contains two bonding electrons. So each radical will donate an electron, an unpaired electron, to form this single bond between them. The second method involves two ions, a cation and an anion. And so both ions will come together to form a single bond, again containing two bonding electrons. So essentially, bond formation is the exact opposite of bond breaking. And another difference between bond formation and bond breaking is that bond formation is an exothermic process, whereas bond breaking is an endothermic process. And here's a table that summarizes the different types of arrow used in organic chemical reactions. So we have the normal reaction arrow here, which basically separates the starting materials or the reactants from the product side. And then we also have double reaction arrows, which are the arrows used in equilibrium reactions. We also have double-headed arrows, and a double-headed arrow is basically drawn between resonance structures. A full-headed curved arrow is for a pair of electrons. This basically shows the movement of a pair of electrons, whereas a fish hook or a half-headed curved arrow is shows the movement of a single unpaired electron. So here's a practice problem. Use curved arrows to show the movement of electron pairs in each reaction. So let's take a look at the first one here. So you can see that we have the reactant side and the product side. And analyzing the structures, you can see that this part of the molecule comes off. So that means that this single bond right here, this sigma bond, is broken. And so the bonding pair will turn into a lone pair and will actually move towards the more electronegative oxygen atom. And for this one, we're going to use a full-headed arrow because it involves a pair of electrons. And so when the two electrons move to the oxygen atom, it will leave this carbon atom positively charged, as shown here. And here's practice problem number 4. Use curved arrows to show the movement of electrons in each equation. So looking at the first one here, you can see the difference in the structure. You can see that we have a carbon to bromine sigma bond. So that means that one of the lone pairs on the bromide ion will attack this electron deficient carbon atom. So this basically shows the movement of electrons, the lone pair of electrons from the bromide ion onto the carbocation ion. So this involves a lone pair of electrons, and so we will use a full-headed curved arrow. And for the second part here, you can see that we have a lone pair of electrons that turn into a double bond, as shown here on the product side. And so that means that this lone pair of electrons will form a double bond with this carbon atom right here. And at the same time, this sigma bond between this carbon atom and this oxygen atom will break and will turn into a lone pair of electrons, which will then be transferred towards the more electronegative oxygen. And so what we have now here is a double bond between these two carbon atoms, and then the oxygen atom will now bear a negative charge because it gained a lone pair of electrons. Bond dissociation energy, or simply bond energy, is the energy required to break a bond, a covalent bond, homolytically. So that means that the two bonding electrons here will split evenly among the two atoms involved in that bond. And since bond breaking requires energy, homolysis is always going to be an endothermic process, whereas bond formation is always going to be an exothermic process. So here's an example of the energy associated with the formation and breaking of a bond. So here we have a hydrogen gas, and the amount of energy required to break this bond between the two hydrogen atoms is 435 kilojoules per mole. So this is an endothermic process. And the formation of the single bond between the hydrogen atoms releases 435 kilojoules per mole of energy. So this is an exothermic process. So here's a table that lists different bond dissociation energies for some of the most common bonds. You learned in general chemistry that bond energy is related to bond length. The shorter the bond, the greater the bond energy. And the longer the bond, the weaker the bond energy. And so you can see here that the bond energy in the hydrogen-fluorine bond is greater compared to the bond energy in the hydrogen-iodine bond. And the reason behind this is because of the difference in their bond lengths. The hydrogen-fluorine bond is shorter compared to the hydrogen-iodine bond, and therefore the energies are different. The shorter the bond, the greater the energy. And you can also see that because of their trend in the atomic size, right? So fluorine is smaller compared to iodine. And so the bond between hydrogen and iodine would be longer compared to the bond between hydrogen and fluorine. And hence you observe this trend in the bond dissociation energies for the halogens. So here's a diagram that shows you the relationship between the size of the halogen and the strength of the bond. So according to the trend in the atomic size, the fluorine atom is the smallest and the iodine atom is the largest. And so that means that the carbon to fluorine bond is the shortest and the carbon to iodine bond is the longest. And so you can see how that's related to the strength of the bond. The carbon to iodine bond is the longest, and so it's also the weakest. Whereas the carbon to fluorine bond is the shortest, but also the strongest bond. So it would require more energy to break the carbon to fluorine bond compared to the carbon to iodine bond. In chemical reactions, there's always a change in the overall energy because bonds are being broken and being formed. Breaking a bond is endothermic and forming a bond is exothermic. So when the overall change in enthalpy is positive, that means that there's more energy being used to break the bonds in the reactants than is being released in forming the bonds in the products. And so when the overall change in enthalpy is negative, there's actually a lot more energy being released to form the bonds in the products than is being absorbed to break the bonds in the starting materials. And in order to calculate the overall change in the enthalpy, we can use this equation shown here. So delta H, or the overall change in the enthalpy, is equal to the sum of the energy used to break the bonds plus the sum of all the energy released to form the bonds. So how do we determine the overall change in the enthalpy for a given chemical reaction? The first thing that you want to do here is to consider the bonds that are being broken and being formed. And then we're going to use the values provided in table 6.2 on page 231 of your book. So here's an example. We have a chemical reaction between tert-butyl chloride and water to form tert-butyl alcohol and hydrochloric acid. So the first thing that we want to do here is to consider the bonds that are being broken and being formed. So you can see here in this tert-butyl chloride that the carbon-chlorine bond is being broken, and then the carbon to oxygen bond is being formed. And then over here in water, you can see that the hydrogen to oxygen bond is being broken, and then the hydrogen to chlorine bond is being formed. And so we're going to look at the values in table 6.2 in order to see the bond dissociation energy between carbon and chlorine in this specific molecule. So you can see that in table 6.2, this bond between carbon and chlorine requires 331 kilojoules per mole of energy in order to break. Whereas for water, it would require about 498 kilojoules per mole. Notice that these values are positive, which indicates that these are endothermic processes. It would require these amount of energy in order to break the bonds. And then in order to form the bonds, energy is going to be released, which will be a negative value because it's an exothermic process. And so for tert-butyl alcohol here, the formation of the bond between carbon and oxygen will release 401 kilojoules per mole of energy, whereas the bond that formed between hydrogen and chlorine, there will be about 431 kilojoules per mole of energy that that's going to be released. And so in order to calculate the overall change in the enthalpy for this specific chemical reaction, all you have to do is add up all the numbers, take the sum of all the numbers to get delta H, and we will get -3 kilojoules per mole. So here we have two examples of redox reactions. We have isooctane and glucose that are being oxidized in the presence of oxygen gas to form carbon dioxide and water. So you can see that both reactions are exothermic because their overall change in the enthalpy are both negative. And so this tells us that both reactions are exothermic. This also tells us that the bonds in the products are much stronger compared to the bonds in the reactants. So here's practice problem number 8. Calculate the delta H for each oxidation reaction. Each equation is balanced as written. Remember to take into account the coefficients in determining the number of bonds broken or formed. And we're already given the delta H for oxygen gas, the delta H for one of the carbon to oxygen double bond in carbon dioxide. So let's take a look at the first oxidation reaction here. So we have methane gas, which is being oxidized in the presence of oxygen gas to form carbon dioxide and water. So the very first thing that you want to do here is to identify the bonds that are being broken and also the bonds that are being formed. And then we're going to take a look at the values in table 6.2 to determine the delta H values for these bonds that are being broken and being formed. So here's the chemical reaction equation again. So you can see that for methane, we need to break 4 carbon to hydrogen bonds total in order to form this carbon dioxide gas. We also need to break the bond between the two oxygens in oxygen gas. And again, that requires 497 kilojoules per mole of energy. And then we're going to take a look at the amount of energy that's released in the formation of a carbon to oxygen double bond. So you can see that the delta H for one carbon to oxygen double bond in carbon dioxide is 535 kilojoules per mole. So this is the amount of energy that's released per carbon to oxygen double bond. And then in water, we're going to have to look at table 6.2 in order to see how much energy is required to form, or how much energy is released to form the oxygen to hydrogen bonds. So for methane here, it requires 435 kilojoules per mole of energy to break this carbon to hydrogen bond. And since we have a total of 4 carbon to hydrogen bonds, we're going to multiply 435 by 4. And then for the oxygen gas, you can see that it would require 497 kilojoules per mole of energy in order to break the bond between the two oxygen atoms. And so that's equivalent to 497 kilojoules per mole. And then since we have 2 oxygen molecules, we're going to have to multiply 497 by 2. And then for the carbon dioxide here, you can see that it would require 535, or it would release 535 kilojoules per mole of energy per 1 carbon to oxygen double bond. And since we have 2 carbon to oxygen double bonds, we're going to have to multiply this by 2 as well. And then for the oxygen to hydrogen bond, this energy that's released is 498 kilojoules per mole. And so because we have a total of 4 oxygen to hydrogen bonds total, right, so 1 mole of water, there's a total of 2 hydrogen bonds, or 2 oxygen to hydrogen bonds. And so we would multiply that by 2. That's a total of 4. So we're going to multiply this value right here by 4. And so now in order to calculate the delta H for this reaction, all you have to do is add up all the numbers. So 1740 plus 994 minus 1070 minus 1992, and we get the total delta H for this specific oxidation reaction. So that would be negative 328 kilojoules per mole. So this indicates that this is an exothermic reaction that releases 328 kilojoules per mole of energy. And for the second problem here, we again have to identify what kind of bonds are being broken and what kind of bonds are being formed. So you can see in ethane that we have to break the bonds between the carbon and hydrogen and also the carbon to carbon bond. So we have a total of 3 carbon to hydrogen bonds, or I'm sorry, a total of 6 carbon to hydrogen bonds multiplied by 2. And then over here we have a total of 7 oxygen molecules, 4 carbon dioxide molecules, and 6 water molecules. So the amount of energy required to break 1 carbon to hydrogen bond is equal to 410 kilojoules per mole of energy. And since we have a total of 12 carbon to hydrogen bonds, we would multiply this by 12. Again, there's 6 carbon to hydrogen bonds here, multiply that by 2, that equals 12. And then we would also have to break this bond here between the carbon and carbon bond. And so this requires 368 kilojoules per mole of energy, and we would multiply that by 2 because we have 2 moles of this molecule. And for the oxygen molecule, it requires 497 kilojoules per mole of energy to break the bond between the 2 oxygen atoms per 1 mole of oxygen gas. And so since we have 7 of them, we would multiply this number by 7. And for carbon dioxide gas, it says over here that 1 carbon to oxygen double bond is formed and releases 535 kilojoules per mole of energy. And so since we have 2 carbon to oxygen double bond per mole of carbon dioxide gas, multiply that by 4, and we have a total of 8. So 8 times this amount of energy. So we would multiply this by 8. And then for water, the amount of energy that's released when the oxygen and hydrogen is formed, the oxygen to hydrogen bond is formed, is 498 kilojoules per mole. And since we have 2 oxygen to hydrogen bond per mole of water, we would multiply that by 6 and we'll get 12. So 12 times this value, and we get the overall energy for released by the formation of the water molecule. So now we would add up all these numbers together. So 5,656 plus 3,479 minus 4,280 minus 5,976, and we get negative 1,121 kilojoules per mole of energy. So again, this oxidation reaction here is an exothermic process which releases 1,121 kilojoules per mole of energy. So bond dissociation energies are useful in approximating or estimating the overall change in the enthalpy of a given chemical reaction. So it tells us nothing about the reaction mechanism, the reaction rates, or kinetics in general. Bond dissociation energies are determined for reactions in the gas phase, but a lot of organic chemical reactions actually happen in the liquid phase. And so again, we only use bond dissociation energies in approximating the delta H of organic chemical reactions. So let's go ahead and switch gears here and talk about kinetics and thermodynamics. In organic chemistry, we synthesize a lot of different molecules, and so in order for that chemical reaction to be practical, the equilibrium must favor the formation of the products, and the reaction rate must be fast enough in order to form the products in a reasonable amount of time. And so this is when thermodynamics and kinetics come into play. Thermodynamics basically describes the energy and equilibrium, whereas kinetics describes reaction rates. So one of the main parameters in determining whether the products are going to be favored or not in a chemical reaction is the equilibrium constant with the symbol KEQ. And the equilibrium constant is a mathematical expression that basically relates the amount of the reactants and products at equilibrium. So let's say, for example, we have this chemical reaction equation here. We have A plus B turning into C plus D. And we always use double-headed arrows or double arrows to indicate that the reaction is in equilibrium, which means that the rate of the forward reaction is equivalent to the rate of the reverse reaction. So we can calculate KEQ, again, the equilibrium constant, by dividing the concentration of the products by the concentration of the starting materials or the reactants, again, at equilibrium. And so with this equation here, that would be KEQ would be equivalent to the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. So when the equilibrium constant is greater than 1, this means that equilibrium favors the formation of the products, which also means that the concentration of the products is a lot greater compared to the concentration of the reactants. You can also say that the equilibrium lies to the right when KEQ is greater than 1. However, when the equilibrium constant is less than 1, that means that the equilibrium favors the formation of the reactants. This also means that the concentration of the reactants is a lot greater compared to the concentration of the products. You can also say that the equilibrium lies to the left when KEQ is less than 1. We also mentioned earlier that in order for an organic chemical reaction to be useful, the equilibrium must favor the formation of the products, which means that the equilibrium constant has to be greater than 1. Another parameter that's used in determining the position of the equilibrium is by using this concept known as Gibbs free energy, which basically tells us the relative energies of the reactants and the products. And so again, another way to determine whether or not the equilibrium will favor the formation of the products is by looking at this concept known as Gibbs free energy, which is symbolized by the letter G. Delta G is the difference in the overall energy between the reactants and the products. So you can see here that the equilibrium will always favor the more stable species, which means lower in energy. And so if the energy of the products is lower than the energy of the reactants, then delta G must be less than 0, as shown here. And so the products are more stable than the reactants. And so in that case, the equilibrium will favor the formation of the products. However, if the energy of the products is greater than the energy of the reactants, then delta G must be greater than 0, which is shown here. And so that tells us that the reactants are more stable than the products. And so the equilibrium would favor the formation of the reactants. So the change in Gibbs free energy is mathematically related to the equilibrium constant by this equation shown here. So delta G is equivalent to negative 2.303 times R times T times log of the equilibrium constant, where R is the ideal gas constant and T is the temperature in kelvins. And so when KEQ is greater than 1, you plug this value into this equation, then we get a negative delta G value, which tells us that the energy is being released, which also suggests that the equilibrium actually favors the formation of the products. However, when KEQ is less than 1, and you plug that into this equation here, we get a positive delta G value, which means that energy is being absorbed, which also tells us that the equilibrium actually favors the formation of the reactants. So here's a table that shows us the relationship between the change in Gibbs free energy, equilibrium constant, and the relative amounts of the reactants and the products at equilibrium. So again, A is our reactant and B is our product. So you can see here that if KEQ is less than 1, then delta G is going to be a positive value. And this also tells us that the equilibrium reaction predominantly favors the formation of the reactants. However, if the KEQ or the equilibrium constant is greater than 1, then the delta G value is going to be a negative value. And this equilibrium reaction predominantly favors the formation of the products. And finally, if KEQ was equal to 1, then delta G is going to be 0. And this tells us that the equilibrium contains equal amounts of A and B. So here's practice problem number 9. Which equilibrium constant corresponds to a negative value of delta G? So we have KEQ equals 1000 versus KEQ 0.001. So for part A here, when KEQ is less than 1, then delta G must be a positive value, greater than 0. However, if KEQ was greater than 1, then delta G is going to be less than 0. And so in this case, we have KEQ equals 1000 which would give us a negative value for delta G. And for part B here, which equilibrium constant corresponds to a lower value of delta G? KEQ of 10 to the negative 2 or 10 to the negative 5? So you can see here that the more positive KEQ is, the lower the delta G will be, meaning the more negative delta G will be. And so the one with the higher KEQ value will have a more negative delta G. So in that case, the KEQ of 10 to the negative 2 will have a more negative delta G value. So here's another practice problem. Given each of the following values, is the starting material or product favored at equilibrium? So for the first problem here, we have KEQ, which is equilibrium constant, which is greater than 1. So again, if we have KEQ that's greater than 1, then that means that the products are favored. So when the equilibrium constant is greater than 1, that tells us that the concentration of the products is greater than the concentration of the reactants, which suggests that we have more products than reactants at equilibrium. Hence, the products are favored. And if delta G is a positive value, then that tells us that the reactants are being favored. Because when delta G is a positive value, KEQ is less than 1. So again, if delta G is greater than 0, then KEQ must be less than 1. And if KEQ is less than 1, then that means that the concentration of the reactants will be greater than the concentration of the products. So in that case, the formation of the reactants is favored. And here's another practice problem. Given each of the following values, is the starting material or product lower in energy? So what does it mean by lower in energy? Well, if we have lower in energy, then that means we have a more stable product or reactant. And so the more stable product or reactant is the favored one. So for the first one here, we have a positive delta G value. So that tells us that delta G is greater than 0, which means that KEQ must be less than 1. So if KEQ is less than 1, then the starting materials or the reactants are favored. And if the starting materials are favored, then that means they are lower in energy. For the second one here, we have KEQ greater than 1. So that tells us that the products are being favored here. And because the products are being favored, then they are lower in energy. And for the third example here, we have delta G that is less than 0. It's a negative value, so that tells us that KEQ must be greater than 1. And if KEQ is greater than 1, then the products are favored, which means that they are lower in energy. And for the last one here, we have KEQ, which is less than 1. And this tells us that the starting materials are lower in energy, which means that they are favored. So we can also use this Gibbs free energy concept in conformations. So here we have phenyl cyclohexane, and these are the two conformations chain conformations of phenyl cyclohexane. So we have conformation A and the chain conformation B. So you can see that B here is the favored one because the substituent is in the equatorial position. This is more favored than if the phenyl was in the axial position, because in the axial position you have 1,3 diaxial interactions, which makes this less stable than chain conformation B. So the delta G here is equivalent to negative 12.1 kilojoules per mole. And so knowing this delta G value allows us to estimate the value of the equilibrium constant, KEQ. And so plugging this into this equation, we can estimate the value of KEQ, which is roughly 100. So this suggests that we have 100 times more B, chain conformation B, than the chain conformation A at equilibrium. And here's practice problem number 12. The equilibrium constant for the conversion of the axial to the equatorial conformation of methoxycyclohexane is 2.7. So we have an equilibrium constant of 2.7. So I'm going to label the first conformation here as A and the second conformation here B. And so the first question here is, given these data, which conformation is present in the larger amount at equilibrium? So for this first part here, A, we have KEQ that is greater than 1. So if we have equilibrium constant greater than 1, then that means that the product is favored. And if the product is favored, that means we have a larger amount of the product. Which in this case, B is favored. And for part B here, is delta G for this process positive or negative? All right, so for part B, again, if we have KEQ greater than 1, then that means that delta G must be a negative value. And in this case, we have negative. And finally, for part C, from the values in table 6.3, approximate the size of delta G. All right, so for part C here, you can see that we have KEQ, which is 2.7. So when you look at the value of delta G, it would be somewhere between 0 and negative 6, because our KEQ value is between 1 and 10. Right, so the delta G value will be between 0 and 6. And negative 6. Okay, so again, that's between 0 and 6. 0 and negative 6.